Welcome back everyone. In this lecture, we will see some more examples of group action and then try to understand the orbit stabilizer theorem in better way. Okay, so let us look at this particular example. Okay, let's start with the group G. Assume G is a finite group. So now what we will do, we will take this particular subset of this group G, call it sigma k, where k is some natural number. Okay, so let's say k is actually between 1 to the order of G. Okay. So then what is sigma k? You collect all the subsets S of G such that the cardinality of S is exactly k. So now what we want to do, we want to make G act on this sigma k, and there is this natural action given by left multiplication. So G acts on sigma k via the following formula. Okay, you take G and then take some S and then you send it to this following subset GS S in capital S. So which is by definition G capital S. So this is just given by the left multiplication. Okay. So this is acting via indeed left multiplication. So now we have the following question. Okay, so why this GS also has cardinality k? So then only the GS has to can be inside sigma k. So let's look at this map from S to GS. So given by small s goes to G small s. Okay, so this map is indeed injective map. Okay, for example, if you look at the image is GS1 is equal to GS2 for some S1 S2 in capital S. So then what will have, you apply G inverse on both sides. So then that will imply that G inverse of GS1 is same as G inverse of GS2. So that will imply that immediately S1 equal to S2. So we have this cancellation, left cancellation in the group. So that makes this left multiplication of this any element is actually an injective map from S to GS. So since this is injective and you can easily see that this is also a surjective, because if you start with some element S dash here, look at G inverse of S dash. Okay. So then you can actually, oh sorry. So this S dash will be some, let me rewrite. So if you take some element in GS, so it is going to look like GS dash, okay, for some S dash inside capital S. So in particularly, so this S dash is mapped to the GS dash. So by definition, this map is surjective and we have verified it is injective. So it gives you bijective correspondence between S and GS. So that means the cardinality of S is same as the cardinality of GS, which is exactly k. So in particularly G acts on this sigma k via this particular action. Okay, let's try to understand this action more closely. Okay, so let us start with the subgroup S of G. Okay, let's say S is a subgroup. So then what will happen to the orbit? Okay, so this S is definitely an element of sigma k. So one can look at the orbit. The orbit by definition what it is all the images of this S under this action of capital G. So that means this is just GS where G in capital G. So this is nothing but what? This is nothing but all the left cosets of this capital S inside G. So this is exactly G mod S. So which is sitting inside sigma k. So for capital S, which is a subgroup, so we have the orbit being exactly G mod S. So now what is the stabilizer? The stabilizer is going to be, so those G in capital G such that that fixes this capital S. So since S is a subgroup, okay, from this GS being S and identity being in capital S, you can immediately see that G must be in capital S, and this is actually if and only if. Okay. So, GS is capital S if and only if G is in capital S. So, that tells you that, so this stabilizer GS is nothing but those G in G such that G in capital S. So, which is nothing but capital S. Okay. So, now you can actually reinterpret orbit stabilizer theorem as follows. So, what is it? Orbit stabilizer theorem says the cardinality of the orbit is exactly the cardinality of the group divided by cardinality of the stabilizer, but the cardinality of the orbit is exactly the cardinality of G mod S. But what is the cardinality of G divided by cardinality of the stabilizer, which is cardinality of G divided by cardinality of S. So, this is actually Lagrange theorem, which comes for free as orbit stabilizer theorem. Okay. So, this is somewhat important action. This kind of action we will see when we prove actually Sylow's theorem. Okay. That is why I am actually defining these actions now. So, now similar to this one can define now using the conjugation, okay, some action of G on elements of subsets of G that are having cardinality K. Again you pick K, you fix K from 1 to the cardinality of G. Now, look at this set, okay, let us call it CK. So, this is those subsets of G, okay, I already named it as sigma K. So, let us use this only. So, we are going to use the same thing. So, sigma K which has cardinality exactly K. So, we will also see in a minute there is another natural set on which also G can act. So, now I want to act G on the sigma K via now conjugation. Okay. So, G acts on sigma K via now conjugation. So, these two are very powerful things, one is left multiplication, another one is conjugation. Again we also have right multiplication, but that is indeed similar to left multiplication. Okay. So, how this G acts on sigma K via conjugation? So, as before, okay, start with some element G in G and then some element S in sigma K. So, then define this G dot S to be just G S G inverse, the conjugate of this S. So, that is by definition G small s G inverse and S in capital S. So, I will leave it you to check. There is this natural surjective map from G from capital S to G S G inverse given by S goes to G S G inverse. So, this is by definition is surjective map, and this is also injective map because we have left cancellation and right cancellation in G. So, this is a bijective correspondence. In particularly the cardinality of S is same as cardinality of G S G inverse. So, now that says that this is an element again in sigma K. So, I will leave it you to check, okay, this indeed defines action of G on sigma K. So, this is something you can verify. So, now what happens if you take the subgroups, okay. So, let us start with S being a subgroup inside G. So, this is just a, let us say, subgroup. So, then what happens to the orbit? The orbit of S is going to be all images of this capital S under the action of capital G. So, which is going to be G capital S G inverse, where G in capital G. So, this is nothing but what? This is the set of all conjugates of capital S in G. Okay. So, now if you use orbit stabilizer theorem, it says that the cardinality of this is exactly equal to cardinality of G divided by the cardinality of the stabilizer. So, let us calculate the stabilizer. The stabilizer by definition those elements G in G such that G fixes this capital S under this conjugation action. That means G S G inverse should be exactly S, but this is nothing but normalizer of this capital S. So, normalizer of S in G. Okay. So, now indeed what we prove using this orbit stabilizer theorem, this number of these conjugates of S in G is exactly equal to the cardinality of G divided by the cardinality of the normalizer. Okay. So, this is something again one can directly prove, okay, but it can be obtained as application of this orbit stabilizer theorem. So, this group action, as I said before, it unifies all these things in very nice way, and then as an application whatever group action that you take, you can immediately see that some of these results for free. Okay. So, now like I said before, we have a natural subset of this sigma k that is actually G invariant. So, let us call that is actually C k. So, C k you can take it to be those now subset of G which is also a subgroup. Okay. Take S be a subgroup of G such that the cardinality of S is k. So, then you can easily see that if S is a subgroup of G, if and only if the conjugate of S is also a subgroup of G. Okay. So, that means because the conjugate is given by the inner automorphism, okay, image of the inner automorphism. So, it must be a subgroup. So, in particularly this particular subset C k is indeed actually invariant subset of this action of capital G. So, in particularly G actually acting on the C k as well. Okay. So, you can directly define the same formula and then verify that that is the action of G on C k, and then the similar stories actually can be verified. Okay. What is the orbit, what is the stabilizer and so on, that can be calculated. So, I will actually give you one more important application of orbit stabilizer theorem. Okay. So, one can use this orbit stabilizer theorem to calculate sometimes the order of the group. Okay. That is very interesting application of this orbit stabilizer theorem. So, let us try to do it in some particular example. Okay. So, we take this automorphisms of some graph and then I will demonstrate so the climb that I made. Okay. So, let us look at this cube. Okay. So, this cube let me draw it. So, this cube looks something like this. Okay. It does not look that great, but still it is okay. So, now let us label them like 1, 2, 3, 4 and then 6, 5, 7, 8. So, now this is a graph. Okay. So, it has 8 vertices. The vertex of this graph, okay, this is a graph that I am interested in. So, this is just these 8 vertices and edges are just given by these edges that joining. So, now recall that what is the automorphism of this graph. So, this automorphism of this graph, so this is just a permutations of these vertices satisfying some property. Okay. Those permutations on these vertices such that, so whenever you have edge from I to j, okay, then if and only if that should imply there is an edge from sigma I to sigma j. Okay. So, this is the condition. So, if you use this E of g as the set of edges of g. So, then you can see that because this is a simple graph. So, that means there is no loop and multiple edges. So, the edges can be just denoted as just a tuple. Okay. So, the let us say E of I comma j is the edge between I and j. So, in particularly E of I j is same as E of j I. Okay. So, because there is no difference between the edge between 1 and 2 and 2 and 1. So, now if you take you can see that the condition that I have written here is same as saying that whenever E of I comma j is an edge of this graph, if and only if E of sigma of I sigma of j, so that is also edge of this graph. Okay. So, that is very important condition for the automorphism. So, these are all permutation of the vertices that satisfies this very important property of this graph morphisms. Okay. So, this is the definition of automorphism of G, and under the composition we have already seen that this actually form a group. So, now we are interested in actually counting the cardinality of this group. Okay. Call this group is G, and then we want to count how many elements are there in this group. So, now what we will do, we make this group act on this vertices. Okay. So, we see G naturally acts on this vertex set 1 to 8. Okay. So, now what we can do, we can easily see that because we are taking all possible automorphism of G. So, you can see that this action that we are talking about here. So, this is again just by permuting. Okay. So, G is a subgroup of this S8. S8 acts on this 1 to 8 by permuting 1 to 8. So, in particularly this G being a subgroup of S8, the same action is there by permuting the vertices it acts. So, now you can actually, I will leave it to you to check this action is actually a transitive action. So, check. So, this action is indeed transitive action. So, that means you can go from one vertex to another vertex by some automorphism. Okay. So, you can just look at the graph, you can see that it can be done. Okay. There are many symmetries here. For example, you can take a plane that cuts this square in this cube into half. Okay. Take this plane for example, okay, that passes through. So, this plane. So, it is cutting this 1, 2 and 3, 4 into half. So, this is with respect to this plane, if you reflect you will be getting one such automorphism. Okay. So, now so using this transitive action, using this orbit stabilizer theorem, you can see that the cardinality of G is going to be exactly. Okay. So, let us look at one particular orbit. So, the orbit of 1 is going to be entire vertex set G. Okay. So, in particularly the cardinality of the orbit is nothing but the cardinality of G divided by the cardinality of the stabilizer. Okay. So, in particularly the cardinality of G is exactly cardinality of the orbit times cardinality of this stabilizer. So, what is the cardinality of the orbit, which is exactly 8, okay, because O1 is nothing but Vg, and then times you have this G1. So, what is G1? So, G1 is nothing but those sigma in G such that it 1 is fixed by that sigma, okay, those automorphisms of G that fixes 1. So, now you can take this G1 again make it act on this vertex set, okay, because G1 is contained in G as a subgroup. Okay. So, we can use the same action. Nah? So, G1 is contained in G. So, G is contained in S8. So, the same action that you have here can be restricted to G, can be restricted to G1. Okay. So, what G1 does? G1 actually fixes this 1, all possible automorphism of this graph which fixes this 1. Okay. But what is the property of this automorphism? If you go back to the diagram, okay, you can see that if you fix this vertex 1, all its neighbors, okay, can be only at most permuted. So, look at this diagram locally, you can see that 1 is here and 2 is here. So, let us see the labeling, 6 is here, okay, and then 1 is also connected with 4. So, mainly 1 is connected with 2, 5 and 4, okay. Only these 3 things are neighbors. So, 2, 4 and 5. So, if you take for example, the image of, you take some sigma in G1, okay, then we know that sigma of 1 is 1. So, what about sigma of 2? Okay. So, if you take sigma of 2, sigma of 4, sigma of 5. So, what properties these vertices should have? So, they all should be connected with 1, because 1 is connected with 2. So, sigma of 1 should be connected with sigma of 2, that means sigma of 1 is 1. So, sigma of 2 is connected with 1, okay. You can see that. So, these are just connected with 1. Okay. But how many possibilities are there? So, we have only the neighbor of this one, that is exactly 3 vertices. Okay. So, only 2 is there, 5 is there and 4 is there. Okay. So, that forces that the sigma of 2, sigma of 4, sigma of 5. So, this is exactly comes from this 2, 4, 5. So, that means sigma just permutes this 2, 4, 5. Okay. So, in particularly if we restrict the action of G1 to these vertices again, okay. So, then if you are interested in calculating, okay, the cardinality of G1. So, then what will happen? For example, I can pick 2, okay, let us pick 2, 2 is in the vertex set. So, then you can actually restrict again the action of G1 to only 2, 4, 5. Okay. So, that can be done. So, restrict the action of G1 to 2, 4, 5, because we just verified that 2, 4, 5 is invariant subset. So, in particularly I am taking 2 from this particular x and then looking at what happens to the orbit and as well as the stabilizer. Okay. So, the cardinality of G1 divided by the cardinality of the stabilizer of this. So, let us denote it by G1 2. Okay. So, let us call G1 2 is the stabilizer of this 2 inside G1. Okay. So, what will be the ratio? That will be exactly the orbit of 2 inside x, okay, this x we are talking about. But if you think about it, I will leave it as exercise. Again G1 action of this action of G1 on this 2, 4, 5, it is going to be transitive action. Okay. One will be able to get permutations automorphism of this G that fixes 1, that takes 2 to 4, 4 to 5 and so on. So, that means the cardinality of this is exactly 3. Okay. So, indeed what we proved that the cardinality of G1 is 3 times the cardinality of G1 that is fixed by, that fixes 2. Okay. So, if you go back to the original equation, then you can see that the cardinality of G is given by 8 times cardinality of G1. So, if you substitute this back, you can get the cardinality of G equal to 8 times 3 times the cardinality of G1 2. But let us recall what is G12. G12 is nothing but those sigma in G1 that fixes 2. But what is G1? So, G1 recall. So, G1 is nothing but those sigma in G such that fixes 1. So, that means if you think about it, then G12 is nothing but those sigma in G such that fixes 1 as well as 2. Okay. So, it fixes both 1 and 2. So, now take this particular group G12 and again make it act on this vertices and then see what happens. Okay. So, now look at this group. So, this is a group. Okay. So, now we can look at neighbors of 1 2 and then see what happens. So, go back to our diagram. Okay. So, let me redraw here. So, this is the so this is 1 2 3 4 5 6 7 8. Let us double check the labeling. 1 2 3 4 5 6 7 8. So, now what we are saying, you have sigma in G that fixes both 1 as well as 2. So, this is 1, this is 2. So, now look at all the neighbors of 1 2. So, that will be 5 6 4 3, that is all. Okay, 2 is connected with 1 4 3 6 and 1 is connected with 2 4 5. So, these are all the numbers that will play important role. So, now if you take this condition sigma of 1 is 1 and sigma of 2 is 2. So, then neighbors of this 1 and 2, okay, they have to play important role. Like now let us look at this 3 and 4. Okay. So, let us look at these vertices 3 and 4. So, you can see that 3 is actually connected with 2. Okay. Then the sigma of 3 has to be again, okay, connected to 2. Similarly, the sigma of 4 that should be connected with 1. Okay. So, you can see that sigma of 3 should be connected with 2, sigma of 4 should be connected with 1. Okay. But 3 4 already has some edge. So, 3 4 has edge. So, that means you should have edge between sigma of 3 and sigma of 4. 1 2 already has edge. So, you should have a picture something like this. So, 1 2 sigma 3 sigma 4. So, this kind of square should happen. Okay, that is the condition. But if you see from the picture, so you have only 2 options for that. Okay, one is you can take the top square, that is 1 2 and then 3 4, and the side square you can take 1 2 and then 5 6. Okay. So, these are all the 2 squares that are possible. So, that means sigma of 3 sigma of 4 either it can be 3 4 or 5 6. Okay. So, I will leave it you to think about. So, there are again more restriction, because if you take sigma of 5 sigma 6, again you can see what will happen to that. Okay. So, you try to actually verify. If you look at this the group G12, okay, acting on again the set of all vertices, okay, then if you look at the orbit of this 3, okay, So then it will have only two choices. Okay. So the orbit of 3, so it will have exactly two choices. So this is something I will leave it to verify. So then you can prove that, so the cardinality of this G12 is going to be exactly equal to the cardinality of the orbit, which is 2 times the cardinality of the stabilizer G1 2 and then 3. So basically what is this G1 2 3? So this is those sigma in G1 2 that fixes 3. Okay. But if you rewrite this in terms of elements of G, you can see that this is those sigma in G such that sigma of 1 is 1, sigma 2 is 2 and sigma 3 is 3. Okay. This is those automorphism of G that fixes 1, 2 and 3. Okay. So, I will leave it to you to think about it and then prove that this is exactly identity map. Once you fix 1, 2, 3, so then you are fixing all other vertices. There is no other option. Okay. This is something I will leave it to you to verify. Okay. So then using this you can see that this is exactly equal to 2. Okay. So if you go back to our formula, so what is our formula says? The cardinality of G equal to 8 into 3 into cardinality of G12. Okay. We just verified that the cardinality of G12 is nothing but 2. So in particularly the cardinality of this G is 8 into 3 into 2. So that is exactly, so 2 power 4 into 3, which is 16 into 3. So that is 30 plus 18, 48. So that is the cardinality of G. Okay. So this demonstrate if you have enough information about the orbit and the stabilizers, one can also compute the cardinality of G. Okay. So this is also very important thing, because in some sense by knowing the information about the orbit, this actually tells us that you can actually kind of come down to some smaller group, and computing the order of that smaller group is good enough to compute the order of the bigger group. Okay. There is lots of symmetry that is going around. So one can use those symmetries and then try to compute everything explicitly for these groups and group actions. Okay, this actually demonstrates the power of orbit stabilizer theorem. So in the next class, I will actually start with proving this Sylow's theorems, which are very important theorems in finite group theory. Okay. So before that, maybe I will do this Burnside's lemma, which is actually very important lemma from the combinatorial point of view. So that actually tells you how to count the cardinality of this x mod G, the number of orbits. Okay. So sometime computing the number of orbits also very important. Okay, I will stop here. We will continue in the next class. Thank you.